everyone, welcome to another Math Club talk. Today's speaker is Bhavesh Pandya, who is a B.Math third year student. His interests are in analysis and probability. Today he will be giving a talk on the Riemann Mapping Theorem. Over to you, Bhavesh.
Okay. So the Riemann Mapping Theorem is a beautiful theorem in complex analysis, which essentially the main problem that the Riemann Mapping Theorem answers is that essentially there's a concept of conformal maps or biholomorphic maps between two domains in C. And so when can there exist a biholomorphic map between two domains? That is the main question that the Riemann Mapping Theorem answers. So can I just state the main problem, which is essentially, which the Riemann Mapping Theorem focuses on. So problem is, given two domains G1 and G2 in C, are they conformally equivalent? Conformally this just means that conformally equivalent, this term just means that does there exist f from G1 to G2 holomorphic bijection? And we denote this as just this. So does there exist a holomorphic bijection from domain G1 to domain G2? That is the question. And the inverse will automatically be holomorphic due to inverse function theorem in complex analysis. Right. So this is the main question here. So holomorphic automatically implies continuous. Therefore, this should at least mean that G1 and G2 are homeomorphic. If they are conformally equivalent. But this is necessary, but this is not sufficient in any case. As an example, I will just look at, this is going to be the main thing. Open unit disk and the whole complex plane. Okay, these two are homeomorphic, but they are not conformally equivalent, which you can see if you know Liouville's theorem. That is, suppose they are conformally equivalent. Suppose then I have f from C to unit disk, which is holomorphic, bijective. A map from C to unit disk which is holomorphic and bijective. But this means that this is an entire bounded function. And any entire bounded function by Liouville's theorem, any entire bounded function will be constant. By Liouville, f is just identically some constant, basically. But that is not possible because it's a bijection to open unit disk. So it is not necessary that if they are homeomorphic, they are conformally equivalent. But okay, this was one example. Another example is Another example is this. If you have annulus, if you have annulus, that is, I will denote by this notation. Here, it's just right. Z such that mod Z bigger than R, less than capital R. And R less than R positive. Just this. So for any annulus, what we can say is that two annuli are conformally equivalent if and only if R by R, the ratio of their radii is equal. So, okay, one direction is clear because if this ratio is equal to this ratio, then you can just scale. That is clear. But the other direction is a non-trivial statement, and this also shows because here, okay, we had their same topologically and something, but okay, one was bounded, one was unbounded in some sense. So okay, you probably cannot say much, but here it is like even more drastic that both are annuli only, but you have some kind of geometric constraint regarding the essentially are they similar or not as geometric objects differing by scaling. So there is this kind of constraint here for them to be conformally equivalent. So it is not as easy as there just being a homeomorphism between these two spaces. Right. So okay, these were just some counter examples or some kind, but I will now
Is it
give some.
necessary for the annuli to be centered at 0?
No, it is not necessary. I just took it for convenience. Just yeah. You can just again translate and scale generally. Right. Yeah. So now I will give some examples which will be useful and which are essentially going to start with fractional linear transformations. So, yeah. This is just going to be map of this form. W being AZ plus B by CZ plus D, where AD minus BC is non-zero. Yeah. Fine. Now here, okay, one thing is a bit evident that if I just try to look at this thing from C to, like if I have to look at from C, then I will need to remove minus D by C for this to be well defined, essentially. So what I would end up doing is, this is a bijective holomorphic map right now. Right now this is a bijective holomorphic map from C minus, you remove minus D by C, and then you go to C, and then you remove A by C. Right now this is being the case if you just look at, try to define it on C. But what for some convenience and essentially it is a bit useful for proving some things, I will define it from C hat to C hat, which is the 1-point compactification or the Riemann sphere. So C hat to again. So from the Riemann sphere to Riemann sphere, I will again define this to be Z is not B by C, right? And infinity if Z is minus D by C, and at infinity I will define it to be A by C. Right. That is fine. Now this is going to be a biholomorphic map on the restriction, and it is also going to be a homeomorphism between these two spaces, essentially. Fine. Okay, so now what we will do is we will what we will see now, yeah, it is right. Better. Suppose Z1 and Z2 are two distinct points suppose they are in C, then what I can have is, I can just substitute Z1 and, okay, one more thing. Fine, okay. Let W1 be Z1 and W2 be Z2. These two are also distinct, and through some manipulation you can get this. The lambda is some constant. Through a bit of manipulation, you can transform this thing to this thing essentially. Right. Fine. Now from here, essentially what we can notice is that if this quantity, like what I will focus on now is, now I will focus on, suppose this quantity is some constant rho, it is a constant, right? Then what is the locus of z? So the locus of z, if this constant was 1, suppose, then it will just be the perpendicular bisector to the line segment joining z1 and z2. Yeah. Right. So if this is 1, then this is the perpendicular bisector. And in particular, it's a line, basically. So this thing being 1 corresponds to a line, and more generally, if this is some constant rho, some constant, then this thing, the locus of z, it will correspond to a circle or a line when it's 1, basically. You will need to do some computation to show this, but that's fine. So the point is, if this is constant, then this implies from here, lambda is a constant automatically, so this will also be constant. Is also constant. So what we can conclude from here is circles or a line are going to circles or a line over here, because if this is constant and this is constant, so you can essentially conclude that from here. I mean, these are circles and corresponding to Z1 and Z2, but you can make a choice of Z1 and Z2 and always get have the corresponding circle or a line, basically. Right. Yeah. Okay, so why did I do this? Right. So, okay, a circle will, or a line is going to a circle or a line. So now I will essentially be getting these conformal maps or biholomorphic maps between two circular domains. Right. So by a circular domain, C is if boundary of C is circle or a line. So essentially we are not going to be distinguishing between circles and lines. Lines will kind of just be a circles which point at infinity. Or if you know stereographic projection, then it's this great circle passing through North Pole, essentially. Right. Now what we want is conformal maps between two circular domains that are, like circular domain can be a half plane, boundary is a line. It can be exterior of a circle, essentially, and it will also include infinity in this case, but yeah, and also disk. These three, essentially. I will first give an example of this. So let's consider the upper half plane, which is just imaginary part is positive. This is the real axis. And I want to map this, suppose this is I and this is 0 and this is minus I. I want to map this to unit disk such that I goes to 0 and okay, let's just say for now that. Then I will just invoke this thing. Essentially what I want now is I to go to 0 and right. And also one more thing, right. The locus of the real axis, as in not the locus of real axis, this is the locus of this thing being 1. So now I will consider this essentially. So I want I to go to 0, so let's just, and say minus I to go to infinity. Yeah, then it should be of this form. Minus I will be going to infinity and I will be going to 0. And lambda is some constant, and okay, you can directly see that lambda should be of form e to the power I alpha, where alpha is some real number, but because here it is easy to see that this should be the case. But more generally, what you can do is you can evaluate at a boundary point this thing. Like you can just say, I want to set this boundary point to this boundary point, and then just substitute the values and find the solve for lambda. I will elaborate this more, but okay, let's just look at this map right now. What I said from that, the boundaries should be corresponding and I should be going to 0. That much is evident. But okay, if you don't want to do any calculation to conclude that this region is going to this region, then what you can do is you can again look at this map from C hat to C hat. What we have is, in the domain, from C hat I am removing the real axis and infinity. Essentially the real axis and infinity. In the domain I am removing this, and now it has two path components. And it is mapping to, again from C hat, you are removing the unit disk. Not the disk, the boundary of the disk. Rather. Yeah. So this has two path components, and this region also has two path components, the interior and the exterior and the navigation. Therefore, and this is a homeomorphism between C hat to C hat. Therefore, restricting to, basically it should map path components homeomorphically to path components. So this path component should go to some path component homeomorphically, and this path component should go to some path component homeomorphically. That is the point. But I is going to 0. So it is evident that this path component is going to the interior, which is an path component. So like this you can just conclude through an interior point and a boundary that this should go here. Okay, so this was just an example. More generally, what you can have is, given two circular domains, let's just denote that by CZ and CW. I want first thing is a correspondence between these boundaries and correspondence between their interior points. That is what I did here. Correspondence between interior point and a boundary essentially. Therefore, for that now what I will say is, given any circle or a line and an interior point in this domain, given say Z, Z naught, and W0. I can find there exists Z0 star and W0 star, Z0 star in C, complement of CZ, and W0 star in the complement of CW, rather in the exterior, more precisely, not just the complement, but fine. Right. Such that the locus of this being some constant and also a constant, okay, and also rho 1, rho 2 constants, rho 1, rho 2 constants, such that the locus of this and the locus of this is the boundary of CZ and the locus of this is boundary of CW. It is easy to see for a line because you can again get the perpendicular bisector, but for a circle you will need a bit of geometry essentially to find this Z0 star and W0 star. But I will just assume for now that you can do this, and given that you can do this, what you will now need to do is correspond an interior point to this interior point and all that. So what I want now is this. I want Z0 to go to W0 essentially, right? Therefore, so now this will be constant and this will also be constant. That is the point. But I will need to choose a lambda such that the boundaries correspond. Basically, because this is a rho 1, then this may not be rho 2 for any choice of lambda, the modulus. Therefore, what I will again do is, I will also pick a boundary point on boundary of CZ and boundary of CW. I will also pick a boundary point and then correspond them. I will send Z1 to W1 and then I can solve for lambda because I just substitute Z1 here and W1 here and solve for lambda. And then because on the boundary this their ratio, it should essentially be a constant. Therefore, once it's the same constant for one boundary point essentially, then it will be the same constant for all boundary points. Therefore, the boundaries will correspond like here. And I already have a correspondence between the interior points. Therefore, like the previous argument, that I have a homeomorphism from C hat minus boundary of CZ to C hat minus boundary of CW. Again, I have a homeomorphism between these two. And each has two path components, therefore, some path component is going homeomorphically to another path component. Therefore, again, once the boundary interior points are corresponding, the corresponding path component should map homeomorphically to that corresponding path component, corresponding to W0. So CZ is mapping conformally onto CW. That is the point. Right. Okay, so this example is related to fractional linear transformations, but there are some more examples which will be a bit, this example will be important. Suppose if you have this domain, this is C and you remove the positive real axis, and can this be mapped to the open unit disk? This is the question. So evidently, I mean, this is not a circular domain, the boundary is not a line, it's just a ray. So can I map biholomorphically onto a disk? That's the question. It's not evident like that you can do this. Like, yeah, if you just look at it at a first glance, then you may not get an idea. But you use the square root. So what you do is you send z to square root of z, and which you can define because you can have r e to the power I theta mapping to square root r e to the power I theta by 2, where theta is between 0 to 2 pi. This is well defined here, and so you can do this, and this will be a conformal map essentially. Therefore, it would map here. It would map on the half plane. This will give you a map on the half plane. And now from the half plane, you have a map to the open unit disk through here, essentially. Therefore, you have mapped this C minus positive real axis to the disk. Now, few more examples. If I have a strip, suppose that is pi I and 0, and I have this region, then the exponential map this takes it to the half plane, because the argument can vary from 0 to pi, and the modulus can vary from 0 to infinity, if you just look at it. Therefore, this thing maps conformally to the half plane, and then a half plane can be mapped conformally to the unit disk. And okay, any two parallel strips are the parallel lines essentially are the same basically. So if you have some other essentially strip, then you can, through a similarity transformation, you can map this to here, and then you can go to the half plane, and then to the disk. Now another thing, right? Now another thing, if you consider lines are the same as circles, so you can also look at circles instead of parallel lines, which are tangent at one point, and this is the region. Suppose this point is 0. If this point is 0, then I can take z goes to 1 by z and map this thing to, because this circle, it will go to a line, because this 0 is going to infinity. So this circle is going to a line, and this circle is also going to a line. And they are parallel because they are only intersecting at infinity. So that is the point. So this region is going to this region of some kind, and you can map this to this strip and then to here. So again, this region can also be conformally mapped to unit disk. So these were the square root example. In some sense, will be used in the proof of the Riemann Mapping Theorem. So that is an important example. Yeah. So I will state the theorem now. Statement of the theorem, that is okay. For G in C simply connected domain, if G is not the whole C, then G is conformally equivalent to the open unit disk. This is the statement. Yeah, I mean, we had already seen that C and open unit disk are different in the first example, but these two are essentially the only examples of simply connected domains up to conformal equivalence. That is a very surprising statement. In fact, even if you ask the statement that what are all the simply connected domains in C or R2, if you ask that question, then also you cannot say that all are basically the open unit disk, because C and open unit disk are topologically the same. So yeah, it does not mean that all the simply connected domains in R2 are the same as unit disk. So even that question is hard to answer possibly. But this theorem answers that, and it is a much stronger statement than just that. Okay, now I will just give a sketch or outline of the proof first. So a sketch. First, what we will do is that if I have G again in C, simply connected, and okay, I will assume G is not C. G is not C, simply connected domain, because yeah, simply connected. Then there exists F from G to open unit disk, which is holomorphic and injective. I have a holomorphic injective map into the disk. So what this will give is, this would give me a biholomorphic map onto the image, basically. So essentially, if G is not C, then I can make G sit inside the disk up to conformal equivalence essentially. So that essentially means that now I only need to attack at this theorem for only the case where G is in the open unit disk once I do this. So now from this point onwards, once we do the first step, we will without loss of generality consider G in open unit disk. And also we will assume 0 is in G. We can do that as well through this mapping only essentially. Now the second step will be that once I have G in the unit disk, then I will consider a family of holomorphic functions. So that will be script F. It will be F from G to the disk. F of 0 being 0. F holomorphic. Let's say F in G, and F is injective. Yeah, I will consider this family of functions, holomorphic functions. This is non-empty because I have assumed G is already inside disk from now on. Therefore, I have the natural inclusion. So script F is non-empty. And right. Fine. The third step would end up being, right. Now we will consider an extremization problem to solve this problem essentially. What we will now consider is fix P non-zero in G. Then we'll consider this problem. Does there exist H in the family such that mod of H of P for all F is script F. So I want a injective function holomorphic such that its modulus at this point is dominating the modulus of fp essentially at for all f in the family. That is what I want. So once we have this function, okay, you can say h will this function, if I have called it h right here. So this h, and now then I will show that h is surjective. Fourth step is h is surjective. So it will be injective because it will be in the family, and in the fourth step I will just show h is surjective, and then we will be done with the proof. So this is the idea, and the motivation for this problem I will give later on, just in the talk only. But yeah. So okay, now let's just start with the first step. First lemma is, like I use the square root here only, right? No. There, yeah. Like I use the square root here, so I will again make use of the square root function essentially in the proof. So what I have is, again, from now on, assume G is always simply connected. So suppose there is a f holomorphic on G, such that f of z is not 0 for all z in G. Right. F is non-vanishing on G, then it has a square root. There exists G in holomorphic on G such that f is G square. Right. And also you can pick it to be G or minus G essentially. At one point you can pick a branch, either a plus or minus essentially. Right. So okay, first I will just assume, I will prove later on that the logarithm of f exists. For now, suppose that logarithm of f exists. That is, there is a, suppose there exists h holomorphic on G such that e to the power h is f. Basically, h is log f. If I have such an h, then what I can do is I can just consider my G to be e to the power half log f. And then G square will be f. If I have logarithm of f, basically. So now I will just show that logarithm of f exists, and then we will get the square root automatically. Right. This one. So for log f, what I will do is, we know in just reanalysis, we generally consider this to define log f or log z or log x rather. And okay, also you can consider this to define log f of x. But so we will do something similar here. So what we will consider is, let's just take a z not in G. F of z naught is non-zero, so there exists W naught in C such that e to the power f of z naught is the first thing, and then now I have this. Now define h to be this function. You integrate from z0 to z and del zeta by del zeta d zeta plus w0. Right. Now this does not depend on the path of integration you take from z0 to z because of Cauchy's theorem. Because G is simply connected and f is non-vanishing. Therefore, f dash by f holomorphic on G basically. Once f is non-vanishing and G is a simply connected domain, so I can always without any dependence on the choice of path of integration, I can define this here, right? So once I have defined this, then what I want to show is e to the power h is f. So let's just consider this function, that is e to the power h divided by f. I will show this is equal to 1. So in fact this is a constant. First I will show that. So if I differentiate this, what happens? Let's just look at the numerator. I get is e to the power h, and then the differentiation of this value h dash. H dash is going to be f dash by f multiplied by f minus again e to the power h times f prime. This is the derivative and it is 0. F cancels and f is non-vanishing, so this division and everything makes sense essentially. So this is a constant, but e, if you evaluate it at z0, e to the power h z0 is e to the power w0, which is f z0. So this is in fact equal to 1 always, because at z0 it is 1 basically. So I got the logarithm, therefore I got the square root. That is essentially the point. So now I have the square root and okay. Now proceed with the first step. That was an injection to open unit disk. Right. So for the first step again, or proof of essentially the first step. Now there are two cases. The first case is G has exterior points. If G has exterior points, then this is easy because I can just pick Z0 in C minus G closure such that I have just this, because there are exterior points, so this is contained in C minus G closure. So there's some delta positive because Z0 is an exterior point. Now what I can just do is I can map Z to delta by Z minus Z0. This map basically just inverts the exterior to the interior of this disk. Essentially this would sort of go here. And it will get centered at 0 and radius 1, essentially. So this will directly give me an injection. This is my F, and F will give me an injection to open unit disk. So this first step is easy, but the first case essentially. Now the second case when G does not have any exterior points. So G is not C, and essentially G closure is C, right? Therefore, there is a boundary point basically because G is not C, whole C. So pick Z0 on the boundary of G, and now I will need to use this square root lemma essentially. Now I consider z minus z0. Say call it f z minus z0, and fz is this is non-vanishing on G. Therefore, I have a square root. So, by lemma, it has a square root. So there is a v from G to G to C. Such that v of v square is f. And v is also injective because f was injective. So right. V is also injective, so I have an injective map. Therefore, I have a biholomorphic map now, basically onto the image from G to V of G. Biholomorphic. Okay, right. Now, what was the point of taking a square root? Essentially, in the previous example which we had, which was this one, we took a square root and the exterior points, they were no longer there. We had some, they were initially not there, and then we got some exterior points essentially by taking a square root. So that is essentially the idea. Now, so v was a square root, minus v is also a square root. But if you look at this, image of G under V and under minus V, their intersection should be empty, because again, this is an injective square root essentially. This is injective, so really minus V will be the other square root of the same value. So it cannot take both the values essentially, otherwise V will not be injective. That is the point. Therefore, and now we invoke the open mapping theorem. So this is true, and V of G and V of minus V of G both will be open. So I have in right. If I just take out V of G's closure, in fact, then this thing contains minus V of G. Because both are open sets. This is an open set, basically, by open mapping theorem. Therefore, I have exterior points. Therefore, my image V of G has exterior points. So my image has exterior points, and this is a biholomorphic map onto the image. Therefore, now by the first case, right here, the first case, now I have a map inside a disk, essentially a biholomorphic map into the disk, some subdomain of the disk, right? So the first step has been concluded essentially now. So the first step is done. Now I can assume G is a subdomain, simply connected domain in the disk having 0. Right. Now, let's just look at this. Okay. Now just look at the fourth step. Now, okay. So assuming third step you can prove and you get an H, then how can you? Basically, now you will need to show that this H is going to be surjective. Whatever H you get from this, from solving this problem once you have solved it. So this H from this will be a map from G to onto the image, biholomorphic map onto the image. Then I want to show it surjective. So if my H of G, if it was a proper subset of open unit disk, then I need to get some kind of contradiction. So for that what I will do now is I will construct something which is known as an expansion. So what I mean is, suppose G is containing 0 in the disk, simply connected domain, and suppose that G is a proper subdomain of the disk. Okay, suppose these things, then I will show that there exists a kappa from G to the disk such that kappa 0 is 0. First thing. Secondly, kappa is injective. And third, mod kappa z because in mod z for all z non-zero because kappa 0 is 0. Right. So once it's a proper subdomain, I will show that there is some kind of expansion of the subdomain. Essentially that, yeah. What I will show that there exists such a kappa, and then I will, once I have the existence of kappa, I will invoke, like if h of g was a proper subdomain, then I will invoke the existence of kappa to get a contradiction. That is the idea. So now I will work towards showing the existence of such a kappa. The idea is essentially that, okay, now I will state, okay, before telling the idea, I will just state the main lemma which essentially motivates the idea. Right. Okay. Yeah, now I will state Schwartz lemma essentially. So that's statement is from a FP holomorphic map from unit disk to C holomorphic, and I have f of 0 being 0. Right, and mod fz for all z. If I have these three conditions, then what I can conclude is two statements. First statement is, and the second statement is this. For all z, non-zero, or yeah, for all z. Non-zero. Yeah. Right. I can conclude these two statements, and also one more thing. What if equality occurs in any one of them? So another thing. Then here, if equality occurs in one, then f of z is of this form, e to the power I alpha z for some alpha real. And if equality occurs in 2, again, if equality occurs in 2 for some z, non-zero, for some z non-zero, then again f of z is of this form. alpha z, again for some alpha real. Right, so if equality occurs on the zero essentially of the derivative fz by z, then it is of this form, and also if equality occurs at some point in 2, non-zero z, for some non-zero z, then also it is of form e to the power alpha z. Ultimately, this means that the equality will occur at all points if equality occurs at any one point, because once f is of this form, then this equality will always occur. So if equality occurs for one point for some z, then it is equality for all points with z is non-zero in the second case, because otherwise it's trivial, and in the first case, okay, it's the derivative. Right. So this lemma, this will essentially help in the construction of this kappa. I mean, that lemma is essentially talking about a contraction. Mod fz is less than equal to mod z. So if equality is not occurring at any non-zero point, then it is going to be strictly a contraction, basically. If equality is not occurring at some point. Therefore, what I want is an inverse of a contraction. That will be an expansion. So this is how I will construct my kappa, but I can get an inverse only on subdomain. Essentially, that is the point. Not on a whole disk. Otherwise, it violates Schwartz lemma itself. So yeah, that's the notation. I will write the details now. So now what I will consider is some functions. Define for C in the disk. For C in the disk, define GC from disk to disk. GC Z is Z minus C by C bar Z minus 1. Okay, so what you can observe, this is a fractional linear transformation again. You will either you will need to do a bit of computations to show it from disk to disk, or yeah, you will need to do some work to show it from onto a disk only. But yeah, assuming that what we have is GC of C, we have a few things. GC is an involution. That is, GC compose GC is identity on the disk. The second thing is again GC of 0 is C and GC of C is 0. Yeah, right, correct. These three things. Now using this GC, okay, so now I need to construct a contraction essentially first. So what I'm going to construct is psi of C, that is going to be J is just the squaring map. J is just so because you can see this as well, psi C of C is C squared, and this psi C of 0 is 0. Fine. Yeah, that's fine. So okay, from this it is evident that the equality is not occurring in the Schwartz lemma basically. If you evaluate it at C, this is C square, mod C square, and this is mod C. So yeah, this is mod C square and this is mod C. Right. So psi C is a contraction. So we conclude Schwartz lemma implies also derivative at 0 is not, it's not mod 1. Yeah, mod of that is not 1. Right. So Schwarz lemma implies this. So, right. Correct. Now we wanted this, we wanted this expansion. So let's do that. So this is this lemma is known as some expansion lemma or square root expansion method. Basically. So say it is second lemma. So now suppose that G is a proper. Just like this. G is a proper domain in open unit disk, simply connected. 0 is in G. Just assume that. And then what we have is, since it's a proper subdomain, there exists clearly. I have C square. There exists C. Right? There exists C in the disk such that C square is not in G. Right. So there will be a point in the disk such that its square is not in the domain. Okay. This will be the case, and once this is the case, what we will now do is, right. Therefore, then there exists V from G to disk such that V square is GC square and V of 0 is C. This is because GC square will be non-vanishing on this domain. Because GC square will be non-vanishing as C square is not there. Therefore, this will be the case. And another thing that we will do is, now we will define this kappa. Kappa will be defined to be GC composed V. And then also we will have then is like this thing. If we have, it is the inverse of Xi basically. Xi composed kappa is going to be identity on G. Right. Correct. This will be the case. And once we do this, we will get an expansion, because it will be the inverse of this contraction, essentially. So let's look at the proof. Right, so first step is evident, because GC square is non-zero for all Z in G. So by lemma 1, we have V from G to disk such that V square is G, C square, and V of 0 is C. Right. Okay. If V of 0 is minus C, then you can take minus V, and this way that's easy. Now you just need to verify this thing. So we just verify it here. Kappa is this, so kappa of 0 will be 0. Okay, one more point. Okay, let's just write it. V is injective as GC square is. V is injective as GC square is also injective. Therefore, kappa will also be injective because GC is injective. So kappa is going to be injective. kappa will be injective and kappa 0 will be 0. Kappa is injective and then just calculate this. Xi c composed kappa, just GC square composed GC composed G. GC was an involution, so this cancels. J is the squaring map, and V square is GC square, so this is identity only. So we are done with this lemma, and now what we have is right. Now kappa from G to kappa of G. So it is a biholomorphic map onto the image because kappa is injective and kappa 0 is 0, all the properties which I stated above. Now mod kappa z, not mod kappa. I know this is identity. Which z? Yeah, this. I know this. So mod z now apply Short's lemma. Z. So this is Short's lemma. This strict inequality because kappa is never 0 on non-zero points, right? So mod kappa z is strictly bigger than mod z for all z non-zero. So we got an expansion, and now now we are almost done. Not almost done. Basically, now if we have such an h exists, we have it written. No, okay, fine. Suppose the h, which was a solution of extremizer problem, holomorphic, right? P non-zero fixed. Then I this h. Now I will just show that this h, if such an h exists, then it will be surjective. So once I have this kappa, that is evident why that would be the case. Right. So suppose such an h exists, then claim is h is surjective. Suppose not, then h of g will be a proper subdomain in the unit disk. Therefore, I have this go to g to h of g, and then because it's a proper subdomain, I apply the lemma. I have a kappa here, such that you go to kappa of h of g, which is inside the disk. It is in the disk, and so kappa composed h will be injective because kappa was, and h is assumed to be injective. So this thing at 0 will be 0 and kappa composed h is injective. Now this is an expansion, kappa. So what I will have is kappa of h of z will be strictly bigger than mod h of z for z non-zero. Now p was non-zero, so you just substitute p. This is true, but kappa composed h is in script f now because it is injective and 0 is going to 0. Therefore, this h won't be the maximizer if it is not surjective. So h has to be surjective. Therefore, once we have that h, we will be done with the proof. Right. So now for that h, right, it will be injective because it was in script f. So for that h we will need two theorems right now. Right, now we need two theorems. First is Montel's. Okay, one more thing. I did not say that. Why do we expect such an extreme measure problem? Like, what is the motivation behind it? So the motivation is that suppose that non-defined script G to be from holomorphic maps from G to the disk such that f of 0 is 0. Right. If we define this family of holomorphic maps, it contains script f, but the point is now that if I look at, suppose there exists capital F biholomorphic, then what we can do is I have the F inverse to the domain, and now for any G where I have this map from unit disk to unit disk. Now G composed F inverse is from unit disk to unit disk, and also it at 0 it is 0. So I can apply Short's lemma. Now I can apply Short's lemma, so what I get is for all z. This implies I substitute f of z now. G of z or z in the disk. Right. So if biholomorphic map exists, then it will be the maximizer essentially. It will be the solution of that optimization problem essentially. If such a map exists, therefore we consider that problem in the first place. Right. So now I will just show the existence of that H. There are two theorems. First is Montel's theorem. If I have a sequence of holomorphic functions on the domain, here G need not be simply connected, just a domain, and suppose Fn is locally bounded then there exists subsequence Fnk and F holomorphic on G such that Fnk goes to F uniformly on compact subsets. On compact right. This is the theorem. Okay. So this theorem will be essentially used for reaching to the maximizer. Because we will go through a subsequence of a sequence which is converging to the supremum or at mod FP essentially. This theorem will be needed, and okay, this theorem just as a, I won't be proving this, but I will just say make a remark that this theorem bears a resemblance to Arzel-Ascoli theorem. Basically, what we have dropped is equicontinuous, but what we can actually being holomorphic, because we already have pointwise boundedness, which was in the hypothesis of in fact locally bounded, which is required, which is in the hypothesis of Arzel-Ascoli. And okay, we are considering compact convergence, so compactness of the domain itself is not needed. We are not talking about uniform convergence, so it's a bit different. But we have pointwise boundedness, but it's not directly saying about equicontinuity at points, each point. But what happens is, being holomorphic and being locally bounded, these two together imply that it's pointwise equicontinuous, essentially. And that happens because of Cauchy integral formula. Just if I write it, f of z, I'll just say boundary of b delta z0 plus zeta by d zeta. Yeah, just the Cauchy integral formula. And if I just consider here fn on if I look at this here, essentially just an outline, not a full proof, but once you will consider this on this region, you can consider less than delta as well, but on less than delta by 2. Once you will consider this, then you can use the Fn being locally bounded on B delta Z0. There will be some ball on which it will be bounded because the family is locally bounded. There will be some ball on which the family will be bounded. That is evident through the hypothesis. And then you will pick that ball and then apply Cauchy integral formula 1 by 2 pi. 1 by 2 pi. And then you will apply Cauchy integral formula. And then you will conclude from here that these fn's have equicontinuity, pointwise equicontinuity, and you have pointwise boundedness. And then you will apply Heine-Borel and a diagonal argument to get to this statement ultimately. Because this is not a compact set, this is an open set, basically. Right. So this is the outline. Now the second theorem I will need is the second theorem I need is this. That is Hurwitz's injection theorem. The statement says that I again have holomorphic functions on a domain and Fn goes to F, it is holomorphic. I again have compact convergence to F, just like in the conclusion of Montel's theorem. I have compact convergence, and also all Fn are injective. Each Fn is injective. Then two things can occur. What we can conclude about F? There are two things. Either first case F is constant, or F is injective. Right. This is the theorem that a limit of injective function can be a constant, or if it's not a constant, then it has to be injective. They are holomorphic functions again. And compact convergence. Right. Again, I won't prove it, but the idea will be that you will first translate the question of being injective to a question of zeros of the function, and then you will apply argument principle, because if I have compact convergence, I can have this going to, let's say, some gamma of delta f, given f is non-zero, right? Given f is non-zero, I can have this to be holomorphic on some small neighborhood, and then this will go converge to this number, and then I will apply argument principle. So that is the point. And in the case, I will first translate the question of being injective to a question about zeros, and then if f will be constant, then that function will automatically be identically zero, and that function will not be identically zero, then f won't be constant, and then I will apply argument principle to conclude that essentially there are no zeros other than that one zero, essentially. This is just a rough outline, but yeah, you have to use argument principle and convert this question of being injective to a question about zeros of these Fn. Right. Correct. So these two theorems. And now, okay, the final proof is now short because I have stated these two. Okay, so now it's easy. Now I have both these theorems. So now what I will get back to the proof of existence of H. So what did I have earlier was, yeah, right, I had earlier this. So now P non-zero was fixed. Therefore, now I look at this quantity. This is evident that I want to look at not this supremum of mod Fp right. It is evident that I want to look at this because I want this to be some h of p, mod h of p for some h in the family. So I want this supremum to be attained essentially here. So now what I can do is I can clearly obtain there exists Fn script f such that, and this supremum exists because they are bounded, because they are onto the disk, not onto inside the disk essentially. Right. So there exists Fn such that mod Fnp converges to mean. And now once I have these Fn's are locally bounded. In fact, bounded. Because they are going to the disk, essentially, the functions, the codomain. So since these Fn's are bounded, therefore by Montel's theorem, I get Fn goes to F, I get a subsequence, basically, Fnk goes to F H or basically from Montel's theorem I get a subsequence converging compactly to some function H, holomorphic function, by Montel's theorem. And then H is not constant. first thing, h of 0 will be 0 because fn0 was 0. Second thing, yeah, h of p, because the natural inclusion, because mod hp is mu, and the natural inclusion map is in the family, so this thing is bigger than or equal to mod p. That is also clear. So these two imply h is non-constant. So h is a non-constant function and fnk are injective. Injective. Therefore, by Hurwitz's theorem, we get h is injective because h was not constant and it's being a limit of injective maps. Right. Therefore, h is inscriptive. Right. H is inscriptive. Yeah. This concludes the proof essentially because the mod hp is mu because it was defined to be this limit. Yeah, mod hp is mu, and so we have mod hp being mu, which is bigger than or equal to mod fp for all fn script f. So h is the solution of our extremization problem. Right. So this concludes the existence of h, and this concludes the main proof, the whole proof of the Riemann Mapping Theorem. Right, and also, okay, I will make few remarks that this proof, it was not constructive at all, apart from the first step, which was involving injecting my domain to the unit disk, inside the unit disk. So apart from that first step, it was not constructive at all. But there is another proof which essentially gives you a sequence of functions to approximate this biholomorphic map, and that arises from the expansion which was constructed. This kappa which was constructed using that essentially functions which are like kappa, which is a compose. Using those functions like kappa, and you just iterate them. Using the iteration of those kappa 1, kappa 2, kappa 3, and so on, you end up getting a sequence of functions which essentially keep on expanding your domain, because kappa expands the subdomain. So you keep on expanding the domain, and in the limit you end up reaching to the whole unit disk. So that is a more constructive method, which is essentially known as Carré-Koebe square root method. I mean, we essentially use that, but we essentially considered a maximization problem and did it this way. But there it is going through a sequence of functions which are more explicit than what we did here, essentially. So yeah, this concludes the proof. And any questions?